Hello everyone, my name is Joel Gao. I will introduce a reliable and interpretable framework of multi-view learning for liver fibrosis staging. I will present the introduction and method sections, and my partner will present the experiment and conclusion sections. The clinical goal of this work is to give a staging score of fibrosis ranging from stage 1 to stage 4. The features we used for staging are the enhanced liver MR images. To deal with this classification problem, we propose to use a deep learning model, which is reliable, interpretable, and could capture features from multiple views. The motivation behind our method is that we want our model to provide human-like reliable predictions. When real doctors stage fibrosis, they will give their staging opinion about which stage the case is. To be reliable, they also express their confidence in their decision. So, we want our deep learning model to output such opinions instead of probabilities. And we want the decision process of our model to be interpretable. So we use logical rules to combine information from multiple views of the liver image, which is similar to the logical reasoning process of humans based on the observations. Now I will dive into the details of our method, which could be summarized in 3 components. First, we use uncertainty-aware opinions to model reliable predictions. Then, the opinions are combined to obtain the overall opinion using interpretable combination rules. Finally, we use multi-view networks to estimate evidence vectors for opinion representation. In the first part, to obtain reliable classification results, we represent model predictions as subjective opinions. Here we use some examples to illustrate what is subjective opinion. When we serve as the reviewer and give opinions about whether a paper could be accepted, we will express our belief, which is the rating score of the paper, and our confidence in the rating. This is called a subjective opinion. When doctors stage fibrosis, they do the same thing. So, in our model, the model's prediction is also in the form of opinions composed of belief scores and uncertainty score. The summation of belief scores for each class and the uncertainty score is equal to 1, which means that the opinion space is defined in a unit pyramid. It can be considered as a generalization of probabilities by introducing second-order uncertainty. To derive the opinion, we use evidence extracted from the image. The evidence is the C-dimensional positive vector encoded by multi-view networks based on input images. Each evidence vector could form a Dirichlet distribution for prediction using equation 1. The parameter of Dirichlet distribution is equal to the evidence plus the prior, which is composed of the base rate and a scalar called prior weight. Then the Dirichlet distribution could be mapped to the opinion through equation 2 and 3. The derivation of these 2 equations is based on the projection of opinions to probability space. The projection is directed by the base rate, which could be considered as the prior distribution if the prior weight is equal to 1. According to equation 1 and 3, we can observe that the core idea of uncertainty estimation in opinion space is less evidence, the more uncertainty. In the next step, we combine the opinions derived from evidence of different views based on interpretable logical rules. We use logic operators introduced in the theory of subjective logic defined for opinion operation. It is an extension of binary logic by introducing distribution and uncertainty. In this work, the subjective logic operator we used is belief constraint fusion, The formal definition is shown in equation 4. Here we use a simple example to interpret the operator. Assume that we have opinions from two different views. If we apply the fusion operator, the combined opinion depends more on the confident one. The uncertainty of the combined opinion is low if at least one opinion is confident. In the last part, I will discuss the details of how to estimate evidence vectors from the liver image. First, we use foreground segmentation and sliding window to extract a global view and multiple local views from the original liver image. Then we use the transformer network to capture features in a global view and convolutional networks to capture local features. The output of multi-view network is the evidence vector used for opinion representation.
Okay, thank Joyao. I'm Yuanye Liu, and I'm going to present the second part, experiment and conclusion. To validate our method's reliability, we compared it with other uncertainty-aware methods based on Bayesian theory. We got a lower calibration error, which means our model is more trustworthy. In addition, we use some visual results to justify the interpretability. Figure A shows a typical sample of stage 4. We can find that the predicted uncertainty is consistent with the circled signs, which are annotated by the experienced doctors. Views with more circles contain more decisive information for staging cirrhosis, and we can see they yield lower uncertainty. In Figure B, which shows a sample of stage 1, the uncertainty in the global view is low since the model needs to capture the entire view to discriminate the stage 1 sample because they have few signs. These two samples illustrate our model could explain which view contains more decisive information for staging liver fibrosis. Then we validated the multi-view modeling with local and global views. We first compared it with other multi-view learning methods. Our model achieved significant improvement in both identifying cirrhosis and substantial fibrosis. Then we performed the ablation study for the roles of local and global views. We found that the local view is important in staging cirrhosis, the stage 4, while the global view contains more useful features to identifying substantial fibrosis. It's reasonable and consistent with our intuition. And we evaluate the effectiveness of the data-efficient transformer instead of CNN. In this work, our framework is reliable and interpretable based on uncertainty awareness and logical-based combination. We are the first to formulate liver fibrosis staging as a multi-view learning problem and incorporate local and global views together to extract complementary information. And we achieve exciting results in both staging cirrhosis and substantial fibrosis. Meanwhile, we want to make further improvements. First, we want to introduce medical concepts to enhance the interpretability. Secondly, we try to customize the base rate to introduce informative prior for the label imbalance problem. That's all about our paper, a reliable and interpretable framework of multi-view learning for liver fibrosis staging. Thanks for your attention.